Welcome back to our series of lectures on chemical bonding. Today we will continue our discussion on molecular orbital theory. In this concluding part, we will take up heteronuclear diatomic molecules, and the session is planned as follows. That is, to begin with, we will briefly review the contents of the previous sessions. Thereafter, we will come down to the today's main theme, that is molecular orbital theory for heteronuclear diatomic molecules. And before coming to this, we will try to recall the treatment for homonuclear diatomic molecules as well. And in the context of heteronuclear diatomic molecules, we will take up three different molecules. They happen to be hydrogen fluoride, and then we will talk about nitric oxide, and lastly we will take up carbon monoxide, and then towards the end we will sum up what we do in today's session. Okay. So, with this brief outline, let us move further and see what we have done so far. What we have done so far is that we started by introducing the concept of chemical bonding and discussed classical theories of this, that is the Causal's theory and Lewis theory and things like that. Thereafter, we moved on to a quantum mechanical approach to chemical bonding, that is in terms of valence bond theory, and we discussed the theory in detail and outlined its limitations. Then in the process, we also took up two things, that is, one is VSEPR theory, and secondly the concept of hybridization to explain the geometry of molecules. And thereafter, we introduced the concept of molecular orbital theory and discussed the approach for homonuclear diatomic molecules. So, that is what we have done so far. Now, in order to move further to heteronuclear diatomic molecules, it will be worthwhile to recall a few things here. That is, in molecular orbital theory, what basically we do. According to molecular orbital theory, what basically we do is we take the atomic orbitals of the constituent atoms which are going to combine together to make a molecule. The atomic orbitals combine together to generate molecular orbitals, and these molecular orbitals are the ones which are spread over the whole molecule. They are delocalized over the whole molecule. That is the first and foremost premise of our molecular orbital theory. The question comes is that how do we get those molecular orbitals? That is obtained by the combination of, that is a linear combination of atomic orbitals, typically called as LCAO approximation. That is, we combine the orbitals linearly and try to get the molecular orbitals. Having got the molecular orbitals, what do we do next is that we distribute the available electrons. That means there are two atoms there, say atom A and B, they have got certain valence electrons with them. So, we pool those valence electrons and distribute them amongst these molecular orbitals there in the order of increasing energies, and in the process we ensure that the Pauli's principle and Hund's rule are adhered to. So, that is the basic approach of our molecular orbital theory. Further, you would also recall that when we talk about LCAO, that is, when we try to combine the atomic orbitals to get the molecular orbitals, we have to keep three things in mind. That is, the atomic orbitals which are combining must have comparable energy. You cannot combine an atomic orbital, one of very low energy, one of very high energy, the two will not interact. And the second requirement is that the combining atomic orbitals must have same symmetry about the molecular axis. That means they can either be aligned with along the internuclear axis, or they are perpendicular, they can overlap laterally. That means you get sigma bonds or pi bonds and things like that. And the third requirement is that the overlap should be as effective as possible, because there is more overlap means you get a better molecular orbital there. And one more thing you will recall, that when we talked about homonuclear diatomic molecules, when we combine atomic orbitals, since they are homonuclear diatomic molecules, that means both the atoms are identical. Since both the atoms are identical, so are their atomic orbitals. So, when two identical atomic orbitals combine, and the resulting molecular orbitals will have equal contribution of both the atomic orbitals. That is a very obvious thing, but that is what we have to state over there, because that has a kind of bearing onto what we are going to take up in today's session there. I think with this little background, we can now move on to the main theme of today's session, that is the molecular orbital treatment of heteronuclear diatomic molecules. Now, in case of heteronuclear diatomic molecules, the scenario is little different here, because what we have is heteronuclear diatomic molecule. There are two atoms there, fair enough, but these two atoms belong to there are different atoms there, belong to different elements over there. Since the two atoms are different what will happen is the combining atomic orbitals will not be identical, because suppose one is say hydrogen atom, one is say lithium or fluorine. So, in the two cases the atomic orbitals will not be identical, which are going to combine together, and once they are not identical, it may so happen that the combining atoms atomic orbitals happen to be similar, but they will differ in the energies there. So, they again they will have a role to play there. Let us try to look this aspect little into detail here. Now, suppose what will happen if orbital differ in their energy? Let the orbital be same. Say there is a 2s orbital here, another 2s orbital here, but when the 2s orbitals of two different atoms combine, they have got different energies to begin with. So, what will be the outcome of that? Let us have a look at it. Okay. Now, let us see what happens in such a case. Let us take two atoms, say atom A and B, and we are talking about their s orbitals, and they have got energy which are comparable, but they are not identical. And when these such two atomic orbitals interact, what happens? Let us further assume that say atom B, the atomic orbital of atom B is of lower energy as compared to that of A. Let us see what happens now. What happens is, so when A and B combine constructively, I get a bonding molecular orbital. That is the shape of the bonding molecular orbital I will be getting there. When the two combine destructively, I will get an anti-bonding molecular orbital. That's what we have been doing all these times when we talked about homonuclear diatomic molecules. But the point which you have to take note of here is that in this bonding molecular orbital, the atomic orbital B, which is of lower energy, that contributes more, whereas in the anti-bonding molecular orbital, the atomic orbital A, which is of higher energy, will contribute more there. So, that is a very important kind of an observation we have to take note of, because this will be important when we go further into discussing heteronuclear diatomic molecules. That this aspect has to be carefully understood, that the bonding molecular orbital will have a contribution of higher contribution of lower energy orbital, and antibonding will have higher contribution of a higher energy orbital there. Okay. Now, let us see how does this combination translate into a molecular orbital energy level diagram. This kind of diagrams you are familiar with by now. Now, what basically this represents is that this is say 2s orbital of atom A, this is 2s orbital of atom B. These two have combined together to give me two molecular orbital, one bonding molecular orbital there, one anti-bonding here. And then this bonding molecular orbital has more contribution of this atomic orbital, which is of lower energy there. And this anti-bonding molecular orbital has got a higher contribution of this orbital, which is of higher energy there. This is a very kind of a general observation which will be of interest to us when we develop the concept further. Let us go further and make note of a few more things there. That is, the shift in energy is lower than that observed in the orbitals for equal energies. What this means is the following. When we talked about homonuclear diatomic molecules, we had two atomic orbitals of equal energy. When the two combined together, we got a molecular orbital of energy say somewhere here, because it will be a stabilized molecular orbital there. Now, if it so happens, now what we are trying to bring home over here is, suppose these two atomic orbitals are combining now. They are of different energies. When the two combine, I still will be getting a molecular orbital here of a lower energy than both of them, but this decrease in energy will be lesser now. When the two were of equal energy, this decrease is much larger. So, that is the point we have to keep in mind there. Now, the extent of interaction depends on the difference in the energies of the atomic orbitals A and B. What it means is this: suppose these two are of same energy as we had in case of homonuclear diatomic molecules, the interaction is very effective. That is why our energy level goes quite low in energy. But now, when the difference is there, if the difference happens to be more, then the interaction will be weaker. Higher the difference, lower is the interaction. Suppose that close by effectiveness is very large, slight difference, okay, effectiveness decreases. You go on increasing the difference between two energy levels, then what happens is that if it becomes too large, there is no interaction at all, and these two atomic orbitals will not be interacting, and they will stay as non-bonding atomic orbitals. They will neither form a bonding molecular orbital nor an anti-bonding one, they will stay as non-bonding there. Okay, that's a new feature here, because we didn't have this feature in case of homonuclear diatomic molecules there. Okay. Now probably we are equipped to take up first molecule, that is hydrogen fluoride. That is, how do we deal with this molecule in terms of molecular orbital theory? Let's look at this. In case of hydrogen fluoride, basically there are two atoms, one is hydrogen, one is fluorine there. And what we have to take note of it here is, that is, the energies of the 2s and 2p orbitals of fluorine are much lower than that of 1s orbital of hydrogen there. This is so because fluorine is highly electronegative. So, say hydrogen atom, say 1s level is here, fluorine 1s will be so down here, and even 2s will be here, 2p will be here. So, even 2s and 2p of fluorine atom will be lower than the 1s of hydrogen atom there. That is, it's an observation which is experimentally borne out, because that we can work out from the photoelectron spectroscopy, that it has been experimentally found to be so. The second thing is, that is, the 1s orbital of hydrogen is symmetry allowed to interact with the 2s and 2p z orbitals of fluorine atom. Let's understand the meaning of this. The meaning of this is that our hydrogen atom is this. This is 1s orbital, spherically symmetrical, and then in the fluorine atom there is one 2s orbital which is spherically symmetrical, and then there are set of 3 p orbitals there. One is pz orbital which is oriented along the internuclear axis. So, this 2pz orbital of fluorine and 2s orbital of hydrogen atom, they are along the internuclear axis, they can interact and give rise to the molecular orbitals there. On the other hand, rpx orbital of fluorine cannot interact effectively with the 2s orbital there. So, in other words, these two are not symmetrically allowed. The only orbitals which can interact between the two atoms are 1s of hydrogen and 2s and 2pz of fluorine there. And then third thing we have to take note of here is, that is, the interaction between 1s orbital of the hydrogen and 2s orbital of fluorine is not there due to large energy difference. 1s can in principle interact with 2s orbital, but the energy difference is so large that this interaction does not take place, and our 2s orbital of fluorine remains non-bonding there. We will come to that as we move a little further. Another observation is, that means effectively what will happen is, that is, the 1s orbital of hydrogen will combine with the 2pz orbital of fluorine to give you two molecular orbitals there. That is what we have been doing all these times there. That's first stage where we are going to get molecular orbitals between hydrogen and fluorine there. Going further, that is how the orbitals will be coming there, because what you are going to have is, this is 1s orbital of hydrogen atom which is spherically symmetrical, and this is 2pz of our fluorine atom. The two will combine constructively to give rise to a sigma molecular orbital there, which is a bonding molecular orbital there. And second interaction possible is that it is this minus this, is a destructive interaction. So, in this case what you will be getting is, you will be getting a anti-bonding molecular orbital there. So, 1s of hydrogen and 2pz of fluorine, the two combine together to give you two molecular orbitals. That is how they are. And the other 2p orbitals of fluorine, that is the px and py, will stay as non-bonding, because they are not going to interact with the 1s orbital of hydrogen atom there. So, what do we get from here? What do we get is the following molecular orbital energy level diagram. Let us understand this now. Let us see that what we discussed so far, how does that translate into this diagram over here. We said that the 2s and 2p orbital are of lower energy as compared to that of 1s orbital of hydrogen. That is how it is shown over here. Number 2 we said was that 1s is symmetry allowed to interact with the 2s and 2pz over there because of their shapes there. But what you find is that this energy of 1s and 2s of fluorine here, they are quite far apart from each other. So, there is no effective overlap between this 1s orbital and this 2s orbital, and this 2s orbital of fluorine atom remains as non-bonding, and that is what you call as 1 sigma Nb. Nb indicates it is a non-bonding molecular orbital there. Then let us move further and see that 2pz orbital from here, 2pz here and 1s, now they are reasonably close in energy. The two will interact and give rise to one bonding molecular orbital, we call it as 2 sigma, and give you one anti-bonding orbital, we call it as 3 sigma star. Star indicates it is an anti-bonding molecular orbital there. So, we get these two molecular orbitals, and out of these 3 p orbitals on fluorine atom, one that is a 2pz has combined with the 1s. This 2px and 2py, they stay as non-bonding again, and since they are coming from the origin is from p orbitals, they will call as pi x and pi y, and they are given subscript as non-bonding there. So, that is the kind of molecular orbitals we have been able to get for our molecule of HF. You should make note of a fact here that when we talked about homonuclear diatomic molecules, we had orbitals like sigma, 1 sigma u, 1 sigma g and things like that. We used the parity of the atomic orbitals there, molecular orbitals there, but in this case we do not do so because the molecular orbitals here to the molecule that is HF is not having any center of symmetry there. So, those things are available only when we talk about homonuclear systems where there is a center of symmetry involved in that. Let us go further and see that what is the molecular orbital configuration of HF molecule. HF, we know that the total number of valence electrons, there are 7 valence electrons in fluorine atom and there is 1 in hydrogen. So, the total of 8 electrons to be accommodated amongst these molecular orbitals there. How are they accommodated? So, there are 2 electrons in 1 sigma non-bonding there, 2 electrons in 2 sigma and 2 electrons each in pi x non-bonding and pi y non-bonding there. So, that is how do we accommodate our 2, 4, 6, 8 valence electrons there, and that can be written as in terms of a molecular orbital configuration there. That is what we discussed in the previous sessions as well. But what is important is that from this kind of a distribution of electrons here, we can work out what is the bond order. Bond order will be half of number of bonding electrons minus number of anti-bonding electrons there. So, there are only 2 bonding electrons there, which is in the 2 sigma orbital there. There is no anti-bonding electron there. So, it will be 2 minus 0 divided by 2 gives me 1. That is HF is a singly bonded molecule there. That is what we get from our molecular orbital treatment as well. Let us move further and see that just to restate, that is the non-bonding electrons do not contribute to bond order there, because when we compute bond order, we just look into the number of bonding electrons, that means the number of electrons in the bonding molecular orbitals and number of electrons in the anti-bonding molecular orbitals. We do not consider the electrons which are in the non-bonding non-bonding molecular orbitals there. One more, this is an important observation here, that is in the bonding molecular orbital, what we got as 2 sigma, the electron density is more towards the fluorine atom, because fluorine energy is lower there, this is higher. So, when the 2 combine, so this bonding molecular orbital 2 sigma has got more contribution from fluorine, thereby, so when the electrons are occupying this level, they will be staying closer to the fluorine atom. That is how we accommodate or account for the polarity of HF molecule there. So, that is how do we represent that, that is there is a slight positive charge on the hydrogen atom, there is a slight negative charge on the fluorine atom there. And of course, the non-bonding electrons, they will remain on the fluorine atom, and that is in accordance with even the Lewis structure. We remember that when you write the fluorine atom there, we show that kind of lone pairs on that. The same thing will hold true here as well. Let us move further and take up the second molecule for today, that is nitric oxide. In nitric oxide, there are 2 atoms, one is nitrogen, one is oxygen there, and the electronegativities of these 2 atoms happen to be 3 and 3.5, which are not very different from each other. Now, since the atoms in NO do not differ much in electronegativities, their MOs also will resemble those of homonuclear diatomic molecules with certain modifications, because they will be roughly similar to what we had in case of homonuclear diatomic molecules, but since the 2 atoms are different, so the molecular orbitals are going to be different, but they will roughly be similar to what we had in case of homonuclear diatomic molecules. And let us see what are the modifications, what are the differences over there. Let us look at that. The energy of the atomic orbitals of more electronegative atom, that is oxygen in this case, will be lower than that of the atomic orbitals of the less electronegative element. That is a matter of fact, we all know that. The second thing we have to take note of here is, that is the molecular orbitals in the heteronuclear diatomic molecule has a greater contribution from the atomic orbital to which it is closer in energy. We showed you that earlier when the two atomic orbitals were combined. So, the bonding molecular orbital had more contribution from the atomic orbital of lower energy there. So, same thing is being restated here. That is what exactly I was trying to convey, that is the bonding molecular orbital has a greater contribution from the atomic orbital of lower energy, and the anti-bonding molecular orbital has a greater contribution from the atomic orbital of higher energy. That is what we established a little while before. Another distinction here is that in case of NO, because those three are general observations for heteronuclear diatomic molecules, but for NO in particular, we find that the 2s and 2p atomic orbitals of oxygen are slightly lower than those of nitrogen, because oxygen is more electronegative than nitrogen. Since it is more electronegative, like we had in case of HF, HF was highly electronegative, the atomic orbitals were far lower there. So, in between the two, nitrogen and oxygen, the difference in electronegativity is not much. Therefore, the atomic orbitals are not of same energy, but are slightly different here. Oxygen is slightly lower than nitrogen there. What kind of combinations are possible there? The 2s orbital of oxygen combines with the 2s orbital of nitrogen to give you 2 sigma orbitals. One will be bonding, one is anti-bonding. That is very obvious to all of us by now. But the important thing is, since the energies are not very different, there will be a reasonable good interaction between the 2s orbitals of oxygen and nitrogen there. The third thing is, that is the 2pz orbital of the two atoms, that is oxygen and nitrogen, they will combine to give you 2 more sigma orbitals there. One will be bonding, one will be anti-bonding. We are just running parallel to what we had in case of homonuclear diatomic molecules there. Then thereafter, what more we expect is, that is the 2px and 2py orbitals of the two atoms, they will combine to give you 4 pi orbitals, because there are 4 atomic orbitals combining, 2 each from oxygen and nitrogen. So, you will be getting 4 molecular orbitals, and since they are going to overlap laterally, we are going to get pi molecular orbitals there, and these 4 will be in the groups of 2 each. There will be 2 bonding and 2 anti-bonding there, and the bonding and anti-bonding molecular orbitals are doubly degenerate. That we all know that. That is, if you just try to look at this, what I just mentioned to you, you find that the overall combining scheme of nitrogen and oxygen is similar to what we had in case of homonuclear diatomic molecules. The only difference lies in terms of the energies of the molecular orbitals, and of course, even the atomic orbitals as well. Let us see how does it translate into some kind of a molecular orbital energy level diagram. Let us see all these points in the terms of a diagram like this. So, what do we see? What do we see is that the energies, that is, these are atomic orbitals of oxygen, they are atomic orbitals of nitrogen here. So, these atomic orbitals of oxygen are having energy slightly lower than that of nitrogen there. That is one fact stated on the diagram here. Then we come to the combinations here. So, this 2s of oxygen and 2s of nitrogen, they combine to give us 2 molecular orbitals, one is bonding, one is anti-bonding. Then thereafter 2pz here and 2pz here, they combine to give you one bonding here and one anti-bonding here, that is at sigma orbitals again. And then 2px and 2py here and 2px and 2py here, they combine laterally and give rise to pi molecular orbitals there. They will be bonding ones, they are the anti-bonding ones. So, that is a molecular orbital energy level diagram for the combination between the two atoms of nitrogen and oxygen. So, they are the possible molecular orbitals we will be getting by their interaction there. The question comes up is that how do we, because the next step according to our molecular orbital theory is, having got the molecular orbitals, we have to accommodate electrons in them. Let us see what kind of accommodation we have here. So, in case of NO, there are total of 11 valence electrons, 5 coming from nitrogen, 6 from oxygen. So, these 11 electrons have to be accommodated in these molecular orbitals we have got there, and that will go in the following way: 2 plus 2, 4 here, 6, that is 2 here, 2 in this orbital and 2 each over there, and there is one single electron over here in the pi 2px orbital there, rather 2p star, because it is an anti-bonding molecular orbital there. So, there are 2, 4, 6, 8, 10, and there is an 11th electron over there. And if I just try to put in terms of a kind of a representation of that, we find that molecular orbital configuration can be given as follows there. That is, the 2 electrons in sigma 2s, 2 into sigma 2s star, and so on and so forth. So, that is the distribution we have, and from this distribution we can work out what is the bond order. To compute the bond order, we see that it will be 1 by 2, that is half of number of bonding electrons, that happens to be 8 in this case, number of anti-bonding electrons, they happen to be 3 there, And so 8 minus 3 is 5, 5 divided by 2 is 2.5. So the bond order for a molecule of NO happens to be 2.5. This unpaired electron in the molecular orbitals we saw, that happened to be in an anti-bonding molecular orbital there, that is pi 2px star, and that orbital is closer to nitrogen atom there. That means the unpaired electron will be located at the nitrogen atom here, and we can represent NO molecule to be something like this, which is a very common and familiar representation of NO. We all know that. Now let's move further and come to the third molecule for today, that is carbon monoxide. In this case, there are two atoms involved. As before, we have got carbon and oxygen. The electronegativities being 2.4 and 3.5. They are not as close as we had in the previous case, but they are still not very far as we had in case of HF. Now again, we will go through the same set of exercise here. That is, in this case, since the atoms in carbon oxygen they do not differ much in their electronegativity, their molecular orbitals resemble those of homonuclear diatomic molecules with certain modifications there. But in this case, the modifications are more significant than what we had in case of NO, because NO, the electronegativities were not very far. In this case, electronegativities are different there, thereby the difference in energy will be more, the extent of interaction will be lesser there. We will remember that as in case of NO, the energy of the atomic orbitals of more electronegative atom, that is in this case oxygen, is lower than that of the atomic orbitals of less electronegative atom, that is carbon. That is fair enough. Second thing is, the molecular orbitals in the heteronuclear diatomic molecules will have a greater contribution from the atomic orbitals to which it is closer in energy. That also we have established number of times. That means the bonding molecular orbital will have greater contribution from the atomic orbitals of lower energy, that is from the oxygen atom there, and antibonding will have more contribution from the carbon atoms there. Now let's come to a particular case of our carbon monoxide now. In case of carbon monoxide, the 2s and 2p atomic orbitals of oxygen are lower than those of carbon because of higher electronegativity of oxygen. That is what we had in the case of NO as well. The second thing we have to take note of here is, that is, the 2s and 2p energy separation in oxygen is greater than that in carbon. This is a very important observation. We will see that how does that translate into our molecular orbital energy level diagram. The third thing is that 2s and 2p z orbitals of carbon combine with 2s orbital of oxygen to give 3 sigma orbitals. This is a very important kind of a differentiation from our homonuclear diatomic molecules and even the two molecules we have discussed so far today, that is HF and NO. In case of NO, the observations were kind of combinations were similar to what we had in case of homonuclear diatomic molecules, but now what we see is that in case of carbon monoxide, we find that 2s and 2pz of carbon, they will combine with the 2s orbital of oxygen there to give 3 sigma orbitals there. One of them will be bonding, one will be non-bonding, and that one will be anti-bonding. We will come to that. The next thing is that is again very obvious one, that is 2px and 2py of the two atoms will combine to give us 4 pi orbitals, 2 bonding, 2 anti-bonding, and they will be degenerate of course. And then what you find is from this analysis here, that is the overall combining scheme is somewhat similar to homonuclear diatomic molecules, but not as similar as we had in case of NO. The difference is in the combining schemes and also in terms of the energies of the molecular orbitals. Let's see all this in terms of a molecular orbital energy level diagram there. What we see here is that, as we know, that here on this side and on this side we are depicting the atomic orbitals. As we mentioned earlier, that is, the energies of these atomic orbitals of oxygen is lower than that of carbon here. That is one fact we are depicting over here. And then when we come to the combining schemes over there, that is the way the atomic orbitals kind of combine to give us a molecular orbitals. In case of carbon monoxide, what we find is that this 2s orbital of oxygen does not interact with any orbital of the carbon atom over here. It stays as a non-bonding orbital there. We just call it as 1 sigma because it is a molecular orbital, and also for the fact that it is coming from the s orbital there, which is non-bonding there. Then what happens is that this 2s orbital here and this 2pz of carbon, these two orbitals of carbon and then 2pz from oxygen, they are the ones which undertake the combination, and since there are 3 orbitals involved in combining, they give rise to 3 molecular orbitals, and they happen to be this one, that is 2 sigma, this is the 3 sigma, and this is the 4th one, that is 2 sigma, 3 sigma and 4 sigma. The 3 molecular orbitals are obtained by the combination of 2s and 2pz of carbon and 2pz of oxygen there. Then we have to take one more note of things here, is that this 2 sigma is a bonding molecular orbital, it has got energy lower than this one. 3 sigma happens to be a non-bonding molecular orbital, again has the same energy as that of the 2pz over there, and this is the anti-bonding molecular orbital there. That is as regards our this combination. Another set of combinations what we are going to have here in this case is, that is 2px and 2py of carbon and 2px and 2py of oxygen. They combine to give us 2 bonding molecular orbitals there, which are pi orbitals there, and 2 anti-bonding pi orbitals over there, which are degenerate, of course. So that is the set of molecular orbital energy levels we get by the combination of atomic orbitals of carbon and oxygen there. Let's move further and see that how do we accommodate the electrons which are there in the valence shells of carbon and oxygen into these molecular orbitals there. As we know that in this case of carbon monoxide, the total number of valence electron happens to be 10. 4 are coming from carbon atom and 6 from oxygen. Total is 10, and that 10 is distributed as follows, that is 2 will be in 1 sigma, 2 will be in 2 sigma, and there will be 2 each into pi px and pi py here, and then 2 electrons will come into this is our 3 sigma orbital there. So that is how the 10 electrons are accommodated. So that can be expressed in terms of our molecular orbital configuration here, that is 1 sigma 2, 2 sigma 2, and then of course this contribution is there. Now on the basis of this we can work out the bond order. The bond order will be 1 by 2 6 minus 0, because there are 6 electrons in the bonding orbitals there and there is nothing in the anti-bonding one there, and that gives me a bond order of 3. That is, in case of carbon monoxide, carbon and oxygen are bonded by a triple bond over there. Okay, I think it's time that we sum up what we have done so far. What we did today is, that is, we started by briefly reviewing the contents of the previous sessions. Thereafter, we explained the molecular orbital approach to bonding in heteronuclear diatomic molecules. We contrasted it a number of times vis-a-vis that in the case of homonuclear diatomic molecules, because the two run parallel, but there are a lot of differentiation there. We highlighted all those differences there, and then thereafter we took up 3 molecules, that is hydrogen fluoride and nitric oxide. Then thereafter in the last we talked about carbon monoxide, and we talked about what kind of atomic orbitals are there and how do they combine, what kind of combinations are allowed, and what is the molecular orbital energy level diagram for them, and then of course what is the molecular orbital configuration and the bond order for each one of them. With this we conclude our discussion on chemical bonding. In the next session we will talk about ionic compounds. Thank you.